In the late 1970s, I was at University College London and working on the theory of using powerful laser light to excite electrons in substances, which then leads to the emission of light with a different colour. If you use a very powerful laser light, then the greater degree of excitation, the more multiple excitations that take place, would lead to much more substantially shifted colours being emitted in the form of photons. So we began to think a lot of molecules are chiral, they have different left and right-handed forms, and maybe that sense of handedness might play into a different response as the harmonic colours were emitted. Later we called this effect chiroptical hyper-Rayleigh scattering. When we developed the theory, it was sound theory, but the kit to run the experimentation simply wasn't available at that time. But then fast forward 40 years and the University of Bath, something new evolved.
Chirality is the handedness of things. The word comes from a Greek origin, literally meaning the hand. If you consider your two hands, they're mirror images of each other. But when you try to superimpose them, they do not fit. Chirality is not only present in our hands. The DNA molecule winds the same way throughout the living world. Chirality is present not only in the DNA, but also in the amino acids that are building blocks of proteins and the sugars. We are chiral. David's theory is really straightforward, but how to prove it? In our case, we used metamolecules. These are tiny little materials that are so small that they can trick light into thinking that they're real molecules. The metamolecules we used were fabricated at the University of Stuttgart in Germany, and they consisted of little springs made of silver. Another key to our success was the use of highly sensitive equipment. Now together, those two elements allowed us to illuminate the metamolecules with light of one color and to detect a very unusual response at a completely different color, at the second harmonic frequency.
Together we developed this range of straightforward, user-friendly techniques with a range of nanotechnological applications, including nanorobotics, the development of optical instruments, and pharmaceuticals.
Our team's diversity is our strength. In our team we have chemists and physicists, theorists and experimentalists. But this work really spans generations, from PhD students to well-established professors.
Modern science can't work without collaboration. We look at a scientific problem from different perspectives, and working together, we can find a problem that was previously thought unsolvable and make it entirely solvable.
I think we've demonstrated that decades-old theories are not just history. They could be the future.